Welcome back, everyone. This is the last day of this lecture series. He's going to talk about hydrodynamic solitons.
Thank you to everybody for being here. So I will give a lecture about hydrodynamic solitons, and I will use the blackboard as much as possible. I will start with a few slides. Of course, if you have any questions, feel free to interrupt me. I do not have a view of the chat, so please ask me directly. So I will speak about some discoveries that were made by John Scott Russell some time ago, not even last century, but the century before. He was a Scottish engineer, and actually he's the one who has invented the steam-driven road carriage, and he also was involved in the design of a gigantic boat that was called the Great Eastern, which installed the first transatlantic cable connecting England to the United States. So one day, he was following one of the canals close to Edinburgh, and this is the story he has written. I was observing the motion of a boat, which was rapidly drawn along a narrow channel by a pair of horses when the boat suddenly stopped, not so the mass of water in the channel, which it had put in the motion. It accumulated around the prow of the vessel in a state of violent agitation. Then, suddenly, leaving it behind, rolled forward with great velocity, assuming the form of a large solitary elevation, a rounded, smooth, and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. And this is the end of the story. I followed it on horseback and overtook it till rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure, some 30 feet long and a foot to a foot and a half in height. Its height gradually diminished, and after a chase of 1 or 2 miles, I lost it in the winding of the channel. Such, in the month of August 1834, was my first chance interview with that singular and beautiful phenomenon, which I've called the wave of translation. So this is the first encounter of a soliton, an hydrodynamic solitons by John Scott Russell. And actually, some years ago, when I was just after my PhD in '95, we went back to this part of the channel close to Edinburgh, and we tried to reproduce these solitons. So today I will discuss this soliton, what are hydrodynamic solitons, and I will try to show directly on the blackboard and tell you what's going on. So I will use the blackboard. So maybe the screen is split because I'm using 2 cameras to have a larger blackboard. I hope it's not too inconvenient, but I will have the opportunity to explain in more details, and I will do some calculations in extenso. So I would like you to have the possibility to look at it. So actually, John Scott Russell went back to his house, and he has a garden, and he made some experiments. So he had a long tank, few meters. He put some water inside the tank, and he has a piece here, which is a piston. And the idea was to study what is the response of the system when you put the piston down into the water, or when you have the piston down into the water, what is the response when you put it up? So John Scott Russell made many experiments and wrote some articles or some reports. And he was able to show that in that first case, once the piston was down, there was a perturbation that he was able to study experimentally in his garden, and he was able to show that putting the piston going toward the water is creating a perturbation that is evolving in the direction of different pulses, typically one, sometimes two, hardly three, that we will call solitons. But the name solitons is much more recent than and was not used by John Scott Russell. So this is the first case, and in the second case, once the piston was down, at the end, he was waiting for the water to be at rest, and the piston going up. What is the behavior of the water? So at the end, the piston is up, in both cases, of course. And in that case, there is a perturbation which is going that way. But he was able to show that in that case, no pulse was able to form, which is not the case, the first case. So this is some drawing of what he was studying in his garden, and he was able to get some results, which were the following. The results obtained by John Scott Russell with 2L, sorry. So an initial condition can lead to the formation of one or two pulses. The waves are propagating with the velocity which is larger than C naught is equal to square root of G times H, where H is the depth of water, and G is the gravity constant, 9.81. Third result obtained by John Scott Russell, the difference between C naught and the velocity V, so the velocity V of the pulse is proportional to the 8 eta of the wave or of the pulse. So this is eta, the height of the wave. We have here h, the depth of the fluid, and the velocity of the pulse is v. Third result, in that case, we do not see pulses. So there is no pulses with the depression. So these results were written in a report that was very debated. By many people, by many famous scientists, and actually people like Airy, who is a famous astrophysicist, astronomer, was also doing some optics, and other people were able to show, or were pretending to be able to show that John Russell was wrong, that it was impossible to have such waves, but they were doing a big mistake. They were neglecting nonlinear terms. So, as we will see, the nonlinear terms are very important, and it's very important to take them into account to be able to understand the formation of these solitary waves. So I will use a definition hydrodynamic solitons are localized solutions or structures that are able to propagate, preserving their shape, and velocity. But so they cannot exist at rest. So it means that if you have a perturbation like that at t equals 0, this is your initial condition. For t positive, you will get the very same pulse which has been propagating towards the left, the right, because of the velocity. And you keep not only the velocity, but the shape is also preserved. But V has to be positive or negative, it cannot be 0. So we speak, so this is a non-topological soliton. So this is a remark. The height of fluid before and after the soliton is the same. So there is no topology differences between both sides of the solitons. So we speak about non-topological solitons. There are other cases, important ones, that I will not discuss here. So this was a discovery by John Scott Russell, and I will try to introduce a solution. So 1.2, interpretation by Korteweg and De Vries. Korteweg was a quite famous mathematician, actually. Both of them are Dutch. Korteweg was the first professor in mathematics at Amsterdam University, and Gustav De Vries was his PhD student. So part of what I will discuss here was his PhD. So for those of you who are doing that PhD or will do that PhD, I hope you will have such success that somebody will speak about your PhD in more than a century. So I will use the acronym KDV for Korteweg De Vries, both names of the who were able to interpret this problem. But the equation describing the existence of solitons is not easy to derive. So I will give the ingredients. It's not difficult, but it's long. It will take me 4 hours to derive the equation. So I will give you the feeling, the physical mechanisms behind the equation, but I will not derive it completely. So the idea is to consider that the system is two-dimensional. So we will consider only the vertical plane, the blackboard. We will use the incompressibility. So the divergence of the velocity field will be equal to 0. I will neglect viscosity. So I could say inviscid. So the kinematic viscosity nu will be considered to be equal to 0. Korteweg and De Vries were using also a rotational condition. So the rotational of the velocity was equal to 0. And another condition is to consider that it is in shallow water, which means that h, the depth of the fluid, is much smaller than the extension of the wave. So using these different hypotheses, it's possible to get the final equation. I will give you at the end the reference of books in which you can get the complete derivation if you want. So introducing C0, which is the velocity of linear waves. Eta is, as we said, is the height of the wave. So 1 over C0, the time derivative of this value eta, plus d eta over dx, where x is the horizontal position, plus 3 over 2h, where h is the depth of the fluid, times eta d eta dx, plus h square divided by 6, and then d cube d eta dx cube is equal to 0. So there are important parameters to see, especially h. You see that h is appearing in the denominator of this term and in the numerator of this term. So if h is large, this term will be more important, and this one will be less important. And of course, if h is small, it's the opposite. You can see also that the first two terms and the third one are linear terms, while here you have eta times the spatial derivative of eta, so it's a nonlinear term. So I will try to play with this equation and to show what Gustave de Vries derived in his PhD. So I will use spatial variables that are slightly different, and I will use one which is x is equal to x minus c0t, and tau and capital T is equal to small t. So here it was small x. Here also it was small x. So using this change of variable, I will be in the moving frame. And it's good to simplify this equation. So you can do it, we can do it because it's rather simple. So the partial derivative with respect to small x, the variable the physical variable that I was using before, is equal by 2. So it introduced two different derivatives with respect to the two new variables, capital X and capital T, and I get, of course, this term is equal to 0, so I get here simply the spatial derivative with respect to small x is equal to the spatial derivative with respect to capital X. And similarly, we get d over dt is equal to d over d capital X dx dt plus d over capital T dt d capital T d small t, and we get minus t naught dx plus dt. So using these new operators, it's possible to simplify this equation. And so we get 1 over c naught times the spatial derivative here, so times minus t naught dx plus dt applied to eta, plus d over capital X eta, plus 3 over 2h eta d eta derivative with respect to x, which is the spatial derivative to capital X, as we have seen here, plus h square divided by 6, the cube eta dx cube is equal to 0. And as expected, this term cancels this one, and so we can just simplify and get 1 over C naught d eta capital T plus 3 over 2h eta d eta over dx plus h square divided by 6 d cube eta dx cube is equal to 0. So this change of variable, which is to be in the moving frame at the velocity of linear waves, tells us that we can get rid of this linear term, and we get an equation in which we have only 3 different terms.
Excuse me.
This is the first simplification. The second one, which is not very important for experimentalists, but which is very important for theoreticians, is to simplify the equation and to put it in a frame that you can deal without taking care of the physics, the dimensions. So the idea is to introduce new variables. So you have the height of the wave that you will compare with respect to h, the depth of the fluid, and we will introduce c is equal to capital X over c naught, and tau, which is capital T over t naught, in which x naught and t naught are effectively a spatial scale and a time scale appropriate to simplify the final equation. So you can check that if C naught is equal to h times square root of 2 over 3. So it's a length scale because h is the depth, and T naught, which is a number square root of 32 over 3 times h over C naught, which is a time scale because we have the length over velocity. Then you use this variable, you plug into this equation, and you get this final equation. d3 over d tau plus 6 phi d phi over d3 plus and this is the standard way to write the Korteweg-de Vries equation. What we call KDV. So I will use this equation and show you how we can derive analytically, and it is quite simple. So analytically, how we can get all solutions, and especially the soliton ones that I would like to clarify here. So once we properties of the KDE equation and its solutions. So it's important to have in mind.
Excuse me, the ping chart is not very clear.
Excuse me?
The pink chalk is not very clear. Can you continue using the white chalk on the board?
You prefer the right one?
Yeah.
Yes, it's strange.
No, the color of the chalk, pink and.
Okay. Okay. I will. Yes, you're right. Thank you. I will use the white. So this KDV equation that I'm discussing today in the context of hydrodynamic application is much more general and could be applied to many different systems, electronic chains, plasma physics, and many others. So the important aspect to understand is that you need a weakly nonlinear system and a weakly dispersive system. So I would like to justify this and to clarify for those who do not know. So let me discuss this equation term by term. So the first one, we have three terms. One which is related to the time evolution. This term which is fairly nonlinear because we have a quadratic appearance of the field phi, and here we have only one phi, so this term is linear. So I would like to explain what's going on for this equation without the third term. So to understand what's going on, it's important to remember what would be the solution of this equation. So in this equation, so it's clearly a simplification of this one by saying that we have here something which is analogous to a velocity. So if it was so simple, we know that for such an equation, the solution would be f of so phi would be a solution of psi minus v2, because v is supposed to be constant. If you plug such an expression for any function f in this equation, you will find that you get 0. But here in that case, it's different. In that case, we have d phi over d tau plus 6 phi d phi over dx. So let me make some discussion. If we discuss this equation with such an initial condition, after some time, we will have the propagation, we will keep the same shape because it is propagating at the velocity v, and nothing is changing. F has to be constant. But for this case, we have 6 phi, so it means that the velocity, the equivalent of the velocity v, is 6 phi. So the lab, so phi is so phi here is the value of the amplitude of this wave. So you understand that if for this equation everything is moving at the velocity v, here everything should move at the velocity 6 phi. So if this part is moving towards the right at a velocity, so let's say it will give you this value. Above, it has to be fast. It has to go faster because it is the velocity, or the equivalent of the velocity would be 6 phi. While below, it has to go with a slower velocity. So the shape will be something like that. Okay, I repeat. If we are using this equation, it means that this shape is moving at the velocity v. But as here we are moving at the velocity 6,5, this part, which is moving towards the right, is moving at a slower speed in comparison to the top of the wave and at a larger velocity with respect to the bottom. So we have here the braking of the wave. No, it's not light wave, sorry. So clearly, the braking is due to the nonlinear term here. Well, actually, it's possible. Using the methods of characteristics, it's possible to get the full derivation of the solution of this nonlinear equation and to derive precisely what is the shape of this nonlinear wave, nonlinear because of this nonlinear term. But I do not want to go into the details. If you want to have more details, okay, of course, I could send it to you. I would like to go now to get the exact solution of this nonlinear equation. But now let's consider what I would call the dispersive term. So instead of removing the third term, I will keep only I will remove the second one. So now we have this equation. We forget the nonlinear term which was in between. This is a linear equation. And so we'll be using plane wave ansatz. So I will look for solution phi is equal to an amplitude A EQ psi minus omega 2. So if I'm destined to look for solution of this type in this equation, I see that I should get minus I omega A exponential plus the third derivative with respect to psi, so it means plus IQ to the power 3 A exponential I with the same thing is equal to 0. So we can get rid of the I, and we can get rid of A, we can get rid of the exponential, and we get omega is equal to minus QQ, which is the dispersion relation. So now imagine that you get the same initial conditions and you are interested in the behavior of this initial condition through this linear equation. This is nothing but a wave packet. A wave packet that you can describe as a sum, an integral, or different phonons, different plane waves, with this shape, the wave vector q, and the frequency omega. So this wave packet, you see that the linear waves have to fulfill this dispersion relation, which is associated to a phase velocity, which is omega divided by q, which is in that case minus q squared. And clearly, this equation depends on q, depends on the wavelength. You see that for large wavelengths, which means q small, the velocity will be small. On the contrary, if lambda is small, you have q, which is large, and you have a phase velocity, which is large. So it means that the wave packet, which is a sum of large wavelengths and small wavelengths, will lose its coherence, and you will get small velocities, small wavelengths that will go much faster with a phase velocity much faster than large wavelengths. So you expect to get something like that. The large wavelengths is moving at a slower wave speed, but with respect to the fast wavelengths. So the pulse loses its coherence because the linear waves have different phase velocity. So this is what we call dispersive effect. We have a wave packet, and everybody inside the wave packet is going at a velocity which is different. And at the end, you have a wave packet that has lost its coherence. It's like a marathon. If you run a marathon, everybody is starting at the same place initially, but some of them are going much faster than the others. So at the end, you have a very huge distribution of people, and the coherence is lost. Here is the same effect. But the coordinate equation is not a nonlinear equation in which you have the breaking. It is not either this dispersion relation. It's different. It combines the two effects. So this is what we call balance between dispersion and nonlinearity. So for such an equation, we find tau plus 6 pi d phi plus we have the nonlinear term, we have the dispersive term, This one is responsible of the breaking of the wave. This one is responsible of the dispersion of the wave. And for such an equation, there is a very interesting balance that, as we will show in a minute, allows the coherence of the wave to be preserved. So there is a balance, and it's important to say that it is a stable balance between dispersion and nonlinearity. So if you start with a wave which is a bit too steep or too high, then the dispersion will play an important role, and then you will reach a stable state in which both terms will compensate, and you reach a state in which the wave will keep its shape. You have this initial condition, and you will get the same initial condition moved by just v, the velocity of the pulse, times tau, the interval between the two snapshots. So it's important to remember that initially we had, no, you do not like initially we had h squared in the numerator, and here we have the h at the denominator before the change of variable. So you see that if the depth of the fluid is changing, the importance of these two terms will change. So if instead of having a flat bottom, you add some oscillations, there will be modification of the two terms. But what's important to understand is that because it is stable, there will be so the perturbation at the bottom, if it is small enough, will not destroy the coherence, and you will have an evolution which will be stable around the mean value of the bottom. In addition, the width of the pulse is in that case much larger than the typical length scale of the perturbation, so it will smooth the perturbation. But in some cases, it could be very different. You understand that if this is going toward the beach, in which h is going toward 0, if h is decreasing, this term will be very important, this one will be less important, and so you will lose the balance between both terms. You will lose the balance, and in addition, you see that the nonlinear term will be more and more important. This one will be less and less important, and you understand that this term will disappear, and you get the breaking of the wave that you know if you go toward the beach, you have a breaking. So at the end, you will have something like that. And you can jump into the wave very close to the beach. And you see this, it's quite easy to understand from these two terms. So now we need to understand how to derive this solution analytically. So second part is to look for solutions of the KdV equation. And I will look first solution with constant profile. So this is we will be looking for solution with shape stay constant without perturbation. So we are interested in solution of phi tau, solution of the equation that we have written several times. The coordinate derivative equations. And we will be looking for solutions that I introduce the velocity v, which is constant, and we expect the wave to be moving at this velocity v. So I will introduce z is equal to c minus v tau. And so I can rewrite this equation as minus v dz phi plus 6 phi tz plus c z is equal to 0. In which, of course, dz is derivative as before. So it is possible to rewrite this equation as d over dz of minus v phi plus 3 phi square plus phi zz is equal to 0. This is not very difficult. So I can integrate, and I will get that the parenthesis is equal to a constant. So I can write this as pzz, the last term, plus 3 phi square minus v phi plus c1 is equal to 0. And c1 is a constant. That we will have to deal with later. Then I will multiply by the derivative with respect to z of phi this equation. And I will integrate, so I will get phi zz times phi z plus phi z and after integration, I will get 1/2 phi z square plus phi cube minus 1/2 v phi square plus c1 phi plus a constant equal to a constant because of the integration. So this is another constant of integration, a priori different, that we will have to deal with. So to solve this equation, I will say that this is a function that I will call v of phi, so that we have 1/2 phi z square plus V phi is equal to theta. And this is what I will call in a minute a pseudo potential. Until now, the solution is very general. The only hypothesis, which is, of course, quite strong, is that I would like to keep the shape invariant. And this is why I introduced this variable z, which is x minus, or actually psi minus beta. So let's look for solitonic solution. Soliton solution. So the soliton solution are solutions in which we are looking for solution which is with this shape. Or we call that this is the depth. But phi is with respect to this position. So we are looking to a special shape, a pulse, with 0 before and 0 after. So we need to have the limit of phi when psi is equal to plus or minus infinity should be 0. See, it's flat. But also the limit of the derivative dz is equal to 0 are both infinities, and the limit of tzz is equal to 0 also at infinity. So we are looking for solution for which we see that from this equation, this term is going towards 0 at the end, this one also, and so we get C1 equal to 0. From the second equation, we see that Tz tends to 0, this term tends to 0, this one also, here C1 is equal to 0, and so C2 is also going towards 0. So if you are looking for localized solutions, you have to fulfill this condition. So condition to have localized solution. So now things are much simpler. This equation tells you that you have 1/2 Tz squared plus T cube minus V over 2 T squared plus 0 is equal to 0. At this stage, you have two different possibilities. We have only one parameter, which is velocity. So you have V, which is positive, or V, which is negative. Now, I will show you in a minute. So this is also what we call V phi, that I will draw. So I will do it like that. So on the left-hand side, I will plot it for V positive and on the right, V negative. So for V positive, close to 0, for V phi, this term can be neglected. So we have a parabola with a prefactor which is negative. So we have the shape which is like that. And for larger value of phi, this term is the most important one. So we get this behavior, and we can plot G phi and we get such a shape. For V negative, the only difference is close to phi equal to 0. We have a parabola which is like that. For a large value of phi, we have the same behavior. And so we see that the only way is this shape. So now this is the way to solve this problem. We need to understand which are the solutions of such an equation. And we will make an analogy. A very simple analogy with a particle of mass unity defined to its position phi, and we will introduce a pseudo-time Z and the pseudo-potential V. For such an equation, you see that you have the position and you have a time derivative with respect to Z. Then it's a pseudo time. So this is the derivative, the time derivative of the position. So it's a velocity square. The mass is equal to unity. So this is nothing but the kinetic energy or the pseudo kinetic energy. And this term is a pseudo potential. So using this simple mechanical analogy, we see we have that the kinetic energy plus the potential energy is equal to the total energy or the mechanical energy, but in that case it's 0. So it's traditional mechanics that we are all familiar with. So we need to solve this problem by considering what is the behavior of such a solution, and can we use this simple mechanical analogy to find the explicit solution of such a pulse. So we see that we start from 0, then we have an elevation, and then we go towards 0. So it means that in the analogy, we have to start from this point, 0, in both cases. So we see that we have several possibilities. If the particle is going towards the left, in the mechanical analogy, it will never come back. It will go down forever. So it will never come back towards zero. So there is, in that case, no solution, no polytonic solution. The other possibility is to go to the right. Then in that case, in the mechanical analogy, you can go to the right. You will go, so you start with zero energy, kinetic energy, the velocity is zero. Then you gain some potential, you transfer potential energy towards kinetic energy. You go up towards that point. And you come back, you go back towards this position zero. So in that case, it seems that we have the possibility to start from zero, to go towards this point, and to come back. So in that case, this is the existence of polytonic solution. So this is for V equal to V positive. For V negative, we start from zero, and we would like the particle to follow this equation. But we see that if we start with the velocity which is zero, at a position phi equal to zero, so no potential energy, there is no mechanical energy, so you cannot move. So you cannot move at all from that position. So there is no solution for V negative. So the only possibility to get localized solution, preserving the shape and moving at the velocity V, which has to be positive, is in that case. We start from zero, we get towards that point, and we come back. So this value, as you can see, is the maximum value of phi. So it's the amplitude A. But I can write it. That point corresponds to that point. The value of phi increases up to A. The value of phi increases up to A, and then come back towards zero, and then come back towards zero. And V is positive. So now it's easy. We know when we get Soliton solution, it's only for V positive, so we can remove V negative. We see that phi is always positive, so no negative solution. We'll come back to that in a minute. And so we can solve this equation. So we can write that dz is equal to p phi d t square minus 2 cube with the square root. So it's possible because V is positive, so this term is positive. So if phi is not too large, the term inside the square root is positive. We are not going to trouble. So if you introduce the change of variable, phi is equal to V h square of Q divided by 2, where h of x is 1 over cosine, hyperbolic cosine of x. From this equation, you get directly 2 lines that are skipped. So you get phi is equal to v over 2 h square v over 4 square root times z. So you see then when x will be large, the cosine will be huge, so the sech will be 0. And when x is equal to 0, you get 1, so the sech will be 1. You clearly see from this that this solution is moving at the velocity v, and because the larger value of sech, the minimum value of cosine is 1, so the larger will be 1, so the amplitude A we see is equal to v over 2. So the larger the soliton, the faster it will move towards the right. And if A is smaller, if you take smaller value of A, you will have something less now, because the width, the typical width of the pulse, in red I will put the typical of the red part, so it could be written as so v over 2 sech square z divided by. So the width is inversely proportional to the velocity or to the amplitude. So you have either a very large excitation, pretty thin, which is moving very fast, or you have a small amplitude red solution, which is wide and which is moving at a smaller velocity. And you get it directly from the whole derivation that we just made on the blackboard. So let me just make a short resume. We have identified localized solution only when V is positive. So what we call, these are supersonic solitons. You remember that at one point we were going from the original frame to the moving frame at the velocity c0. Here V is positive, so it's moving with a velocity which is larger than 0, which means supersonic, because we are already in the frame moving at the velocity c0. This, in the original frame, these solitons are moving at the velocity c0 plus. So let me just recall that A is equal to V over 2, so that phi is the amplitude times sech square square root of A over 2 psi minus, so Z, which is psi minus V tau, and V is equal to 2A tau. So you have, as we have seen, either large and small solution, or a large and thin solitons with a velocity which is much larger. So in that case, the larger, the faster. And if you come back to the original physical quantities, so coming back to the original physical quantities, we get eta is equal to eta naught h squared 1 over 2h 3 eta naught over h squared x minus c naught 1 plus eta naught over 2h times t. So clearly we get a velocity which is larger than c naught because eta naught is positive. We see also the effect of the value of h. If you have a deep fluid, h will be large, so the difference with respect to the c naught will be small. If you have a very shallow fluid, then this term will be much more important. Okay. So I'm almost towards the end. I would like to show you some pictures.
Excuse me, sir.
So I guess you have. So this is a typical wave. That is, it's a picture that you can get from many different beaches. Where you see some perturbations that are reminiscent of what we just derived. Here on the left, you have Korteweg de Vries, Diederik Korteweg. On the left, who is this professor of the first professor of mathematics in Amsterdam University. And on the right, Gustav de Vries is a former PhD student. I wanted to show you through these two pictures, where it is not perfect, that some waves could be propagating as solitons in calm sea, but also in choppy sea, because of the stability that we just derived. I didn't prove it, but it's possible to do so. And so this aspect was clear. One aspect that I would like to just discuss is what is quite interesting to understand is that, as we have seen, the velocity depends on the depth of the fluid. So, excuse me, it's written in French. Plage means beach in French, and fond marin means the bottom of the sea at time t0 and at a larger time. So if you imagine that you have a wave which is arriving along that line, so perpendicular to the beach, because here the depth is larger, the velocity will be larger, and here it will be smaller. And so immediately you see that if the wave was arriving parallel to the beach, because of this effect, it will arrive always perpendicular to the beach. And so this is why it's very dangerous when solitons are generated by earthquakes, because in all cases, at the end, they will arrive towards the beach. This is also a numerical simulation that is showing that large amplitude and thin solitons could be faster than small amplitude and wider solitons. So this is a typical shape that you can get as the time is evolving. You see, the larger, the faster. In some sense, it's different from what you get on the marathon line. Usually the winner is small. This is an experiment that has been prepared in Dijon, in Burgundy. So this is in a long tank. This is the evolution of the wave that you can follow with the camera, and you see that it is preserving its shape. Of course, in that case, dissipation cannot be neglected. There are some effects, but you see that the propagation is okay during a very long time. This is a long tank that they were able to get. You can study the collision of such excitation also. Another experimental results, some experimental results that are quite interesting to get. This is some measurements that were made in another canal in Lyon, which is several tens of meters long, in which you have different props, conductivity props, referred by this value C. So you generate a wave on the left-hand side of the tank, and you look for the propagation of the wave. And you see that depending on the position of the conductivity probe, this is the first one, the second one, the third one, the fourth one. So this is 1, 2, 3, 4. So you see that the propagation could be, there is some dissipation as it propagates along the tank because of the dissipation, but you see that the shape is more or less well preserved. So it's not perfect. You have a damping term that you should add to explain the evolution, but you see that it is quite nice. And using this tank experimental results, it's possible to compute the velocity and to check that indeed there is a term which is proportional to the linear waves, what I call C naught on the blackboard, plus a perturbation that depends on the height of the solitons. And actually, this measurements is comparing on the left-hand side with respect to square root of GH, with respect to C naught, and on the right-hand side is looking for the perturbation, the difference between the velocity measured and this C naught. And you see that clearly it is behaving with a linear evolution as we just derived analytically. One point that I would like to emphasize is that these waves are solutions of a field equation. So they are localized in space, but it's possible to look for collisions of such objects. So this is a picture that was taken on the beach, where you see two different lines, which are the signatures of the two different solitons, which are propagating in slightly different directions, and that are colliding in the center of the picture. This is the case where the amplitude is rather small. On this picture, you see the collision of two different waves, which is leading to a collision region in which the amplitude is much larger. And finally, this object could be fun to surf on. This is a typical image that was taken in the south of France, where you have surfers playing along such what we call mascaré in French, which is soliton trains that are generated by the effect of the tides over this river, which is called the Garonne. There are similar solitons close to the on rivers. One is very important in Amazon, in the north of Brazil, in which people are able to follow the waves during several kilometers on the Amazon River. Okay, I think this is the end of the talk about the introduction towards hydrodynamic solitons, solution of the Korteweg-de Vries equation. And if you have any questions, I would be pleased to answer to them. Thank you very much.
Excuse me, sir.
Hello.
Yes.
I have a question regarding why it is not possible to have a depression type soliton in the surface gravity wave. You are showing the bulge type of soliton, like solitons. Like in the first slide, in experiments by the first experiments, when the plunger is pulled out from the tank, there was one depression, but it was not turned out to be becoming a depression type soliton.
Yes, I will skip. So I'll try to use.
Okay.
So I guess you see it now. You remember when we saw a negative value would be going towards the left, and we showed that it's not possible. You remember this case?
Yes, yes.
So this is a negative value of phi. So this domain is the free part, the mechanical particle. The analogous mechanical particle is going towards the left, towards negative value of phi. It will never come back. So we proved together that there is no negative soliton possible from scratch. So this is for the Korteweg-de Vries equation that I just showed. Actually, if you play if you are looking for the behavior over water, if you are doing with mercury, the surface tension will play a different role, and then in such a case, for mercury, so you may have depression solitons that are able to move. This is also the case for stratified fluids. If you have 2 layers of fluids with the density ρ1 smaller than the density ρ2, which is larger, then in that case, you may have depression solitons. But for water, we have shown that it's not possible. The only possibility is to move inside this potential well, and so phi is positive. Is it clear?
I have confusion about mercury. You mean that in mercury as the working fluid, one can expect a depression type soliton. That's what you said.
There is a paper by Falcon, Laroche, and Ford. Actually, it was done in my laboratory here in Lyon. So I don't know the reference by Earth, but if you are interested, there are not so many papers with these three names. You will be able to show, to read how one can excite waves in Mercury and how we can start study propagation of solitons. And actually, it's clear that you get the question here.
Okay, that means some type of surface tension or capillary effects will be there. That's why it is happening.
Exactly. Exactly. Okay. Actually, it will change the sign of the dispersive term. The D3, 5 over xi. This term will be in front will be negative if you change, if you have small enough depths of Mercury. Look to this paper. It's, I think, quite well explained.
Okay, thanks.
Any other questions? Okay, thank you to everybody.
Hello, sir.
Yes.
Sir, there are questions in the chat box.
A small query. Before approaching the beach, can the same wave disperse? But as h is high, the dispersive term has its front h square. So if h is decreasing, the dispersive term is decreasing in importance. On the contrary, the nonlinear term has 1 over h in front. So the nonlinear term is more and more important. So as it approaches the beach, the soliton will break, as we have seen in all videos. So no, on contrary to what you say, Raja, the dispersive term is less important close to the beach. It is more important later. If I understood you correctly from the plot of, even if there is a localized pulse of amplitude less than A, is it at a time when? Yes. Yes, answer to the second question is yes. What is the effect of viscosity? So the effect of viscosity is to damp, of course, to damp the motion. And actually, the amplitude is usually slightly decreasing, as we have seen in the experiment. And usually, of course, there is a width which is increasing, because there is the width is inversely proportional to the amplitude. How solitons are generated into the ocean. I will try to show you this. So, for example, in 2004, the big problem was close to Thailand. In that case, this is a typical case in which the bottom topography went up by 1 meter, which is not much, but by 10 meters, which is not huge with respect to the depth of the fluid, but over typically 100 kilometers. So this is an experiment which is very similar to the experiment by John Scott Russell. Of course, the piston was not going from the top towards the bottom of the tank. In that case, this is the bottom of the tank which is going up, and which is providing an impulse in the water that is able to propagate, and was able to propagate over very huge distances, because it was able to, as we have seen here, it was able to start from the Thailand and going towards Africa. There is an island in France which is called La Réunion, very close to Madagascar, which is I don't know, 5,000 kilometers and away from the epicenter. And it was clear that the arrival of the solitons in 2004 was clearly seen in data. So this is how tsunamis are formed when the seabed is able to rise up. I don't know if there is other questions.
Sir, from your previous lecture, how can from your previous lecture on nonlinear internal waves, how can numerical viscosity affect the triadic instability?
Can you repeat, please?
From the previous lecture on nonlinear internal waves, how can numerical viscosity affect the triadic instability?
Numerical viscosity can affect triadic instability. So you are coming back to the previous lecture.
Yes.
In principle, numerical viscosity should be not coming into play. So if you are careful enough and you are doing numerical simulation, it should not. You should be able to avoid numerical viscosity. So this is not a physical effect.
Okay. So it can suppress the instability, is it?
Yes, it can suppress, but it means that your code was not well prepared. So you have to be careful. So there is a question about the inverse scattering transform. I would need an additional lecture. Yes, it's possible to present a method which is called indeed inverse scattering transform that is able to provide the number of excitation, the shape, the velocity from the initial conditions. If you want, I wrote a book. I don't know where it is. Maybe I will show you this later. So I wrote a book in which there is a chapter which is about inverse scattering transform for quantum vector equation, which is presented, I think, at a low level, and you can get and understand everything with basic physics and mathematical background without any problem. So in this book, we discuss not only hydrodynamic solitons, but also other ones. So, for example, it's possible to get what we call kinks, in which you see this is a chain of pendulum, in which you have pendulum which are moving from the bottom towards pi, towards 2 pi. I can show you here. This is a video. This is my hands on the right. You see the pendulum which are coupled by some spring, and it's possible to generate perturbation which are moving. You see that they are localized in space. They are called solitons. Contrary to quantum vector solitons, before and after, it's not the same state. It's between it's 0 on the one side, 2 pi on the other one. So they are called topological solitons. This is, for example, another topological soliton. This is snow. So at least in Madras, you don't have a lot of snow. In other places in India, of course, you have snow. But you see that the snow is going down, then going up and coming back. And so this is a case where we have a frozen snow soliton. So you see this is a topological solitons. In some sense, it's not moving. So contrary to non-topological solitons as hydrodynamic solitons, you can get topological solitons which are not moving. For a fluid, if you have a bump, you can easily imagine that it cannot stay coherent if it is not moving. For topological soliton, is different. And this is typical images that I like, where you have different shapes. So you have hydrodynamic solitons on the beach. You have this snow frozen soliton. You have these patterns that you are able to see from satellite images from space, which are due to the stratification of the fluid. We have also hydrodynamic solitons on river. This is in Australia. And I was once I went to Shanghai in China, and I liked this this building where I could see some solitons, but it was just for architectural way. Okay, I don't know if there are any other questions. Okay, I thank you very much. It was a pleasure for me to give these two talks. I would say that it was a pleasure to be in India 1 year ago with my colleague that are also your lecturers, Mani Mathur here on the center, and Anubhav Roy, and their colleagues and friends, Samin. So it was 1 year ago. We were doing a marathon in Chennai. So it's a good souvenir. I would like to conclude by this and saying have a good day to all of you, and I hope to meet you somewhere. If you have any other questions, you can send me emails. Thank you and have a good day.
So are there any other questions? This picture feels like from a previous life theory. The year has been so long.
Yeah.
Okay, if there are no other questions, I would also like to thank Thierry again for the 2 wonderful lectures. And please do log back in at 6 p.m. where Philippe will continue from where he left off yesterday, and that would be the last lecture for the series. Anubhav, is there anything to add?
No, that would be it.
Thank you very much, and have a good day.
Thanks, everyone. Thank you, Thierry, again. So, Anubhav?
Yeah.